Hey everyone, and welcome. In the world of computer science and system design, pretty much everything we build rests on a foundation of logic. It's that simple idea. If some condition is met, then a certain action happens. It is the absolute bedrock of every single program you will ever write.
So, today, we're going to untangle the surprisingly confusing language that wraps around this very simple concept. Here's our game plan. We'll start with the puzzle itself, then we'll set up our logical anchor, the conditional proposition. After that, we'll decode those tricky phrases, look at some logical relatives, see it all in action in actual code, and finally, we'll pull it all together with the big unifying principle. All right, let's get into it. So here's the real issue, right? The logic underneath it all is actually super straightforward. It's the way we talk about it in English that can be a massive hurdle.
I mean, we all get this, right? It's a classic if-then statement. If the department gets the cash, then they hire someone. Simple, clear, no confusion whatsoever. But this is where things get messy. You see these phrases pop up in technical requirements and textbooks, and they all kind of feel like that same if-then logic, but the wording just trips people up all the time. Do they mean the same thing? Are they different? Well, that's the puzzle we're going to solve today.
So, to untangle all this language, we first need to set up a solid foundation. A logical ground truth that we can always come back to no matter how confusing the words get.
And this is our anchor, the conditional proposition, written as P implies Q. P is our hypothesis. That's the if part, the condition we're checking. And Q is the conclusion, the then part, the thing that happens. This is the formal, rock-solid structure for any if-then statement.
Now, don't let the table scare you. The only thing you really need to remember here is that the whole statement, P implies Q, is only false in one very specific situation, when the if part, P, is true, but the then part, Q, turns out to be false. That's it. It's like a broken promise. In all other cases, the logic holds up. Let's make this real with an example we can stick with for the whole explainer. Let's say P is a user has admin rights, and Q is the user can access the server. So our core rule, P implies Q, becomes if a user has admin rights, then they can access the server. From here on out, we're going to treat this as our unbreakable system rule.
All right, our anchor is set. Now, let's start decoding those confusing phrases. We're going to start with sufficient and necessary.
First up, P is a sufficient condition for Q. So what does sufficient really mean? It just means enough. That's it. Knowing that P is true is enough information for us to know for sure that Q has to be true. In our example, having admin rights is sufficient to get server access. You show me that you're an admin, and that's all I need to know. It's enough. You're in.
Okay, now for the one that usually causes the headaches. Q is a necessary condition for P. Notice how the letters are flipped around in the sentence. Necessary just means required. It's a prerequisite. So if that required condition isn't met, if you can't access the server, which is not Q, then there's no way you can possibly be an admin, which is not P. Server access is a required part of being an admin.
So here's the bottom line. Saying P is sufficient for Q means P is enough to get you to Q. And saying Q is necessary for P means you can't even have P in the first place without also having Q. You see? They're just two different ways of looking at the exact same logical coin.
Let's keep building on that. We're going to look at how this all connects to two other key concepts, the converse and the contrapositive. Nailing these down is a huge step to mastering logical statements.
So the converse is pretty simple. It just flips the original statement. If you have P implies Q, the converse is Q implies P. Easy. But the contrapositive, now this is where the real power is. It not only flips the two parts, but it also negates them. So the contrapositive of if P, then Q becomes if not Q, then not P. And here's the secret sauce. This is a fundamental theorem in logic. A conditional statement is always logically identical to its contrapositive. They mean the exact same thing. So, if you have admin rights, then you can access the server is 100% the same as saying, if you can't access the server, then you don't have admin rights. This little trick is an incredibly powerful tool for breaking down complex rules.
Okay, I know this has been a little abstract, so let's bring it back down to earth. Where does this stuff actually show up when you're writing code?
Well, every single if statement you've ever written is a conditional proposition. In this little piece of code,
the hypothesis is x is greater than 3 and x is less than 10. The conclusion is print the statement. So when we test it with a value like x equals 5, the hypothesis is true, so the action has to follow. It's the most basic building block we have for controlling how a program flows.
Here's a fantastic real-world example. This is a rule that pretty much every software team lives by. The hypothesis here is the program does not pass all test cases, and the conclusion is it is not ready for deployment.
Now, let's use that awesome tool we just learned about, the contrapositive. Let's flip and negate that original rule. What do we get? If a program is ready for deployment, then it must have passed all test cases. See how much clearer that is? It takes an implicit requirement and makes it explicit. It's the same exact logic, just framed in a way that's much more useful for making a decision.
Okay, we've looked at the definitions, we've decoded the tricky phrases, and we've seen it in action. It is time for the grand finale, where we see how all these different puzzle pieces finally click into place. And here it is, the grand unification. All 4 of these statements, if P then Q, P is a sufficient condition for Q, Q is a necessary condition for P, and yes, even the weird one, P only if Q, they are not different logical ideas. They are simply 4 different English sentences to describe the exact same relationship. P implies Q. They are completely, totally, 100% interchangeable. So when you see one of these, you can just mentally swap it for whichever version makes the most sense in your head. And this isn't just some academic brain teaser. It's about being precise in our work. So the next time you're reading a technical document or trying to debug some logic, don't let the words throw you off. Just focus on that underlying proposition. And that really leaves us with a final question for you. How is this going to change the way you read your next design doc or tackle your next debugging session?